get some more in a moment. Here's some more. We'll see if I run out or if I don't run out. I think it's right. And then I'm sending another one around this way. You have two handouts today. Take one and pass it around. Does anybody lack a midterm? Does anybody lack a midterm? A few quick reminders. The midterm is due. The back one there. And if you need more, come visit me during office hours. Who else needs midterm? Ladies and gents, if you like the information over the summer so far, gentlemen, don't talk over it. Don't talk over it. If you feel like the information of the summer is very zippy, today, here's the good news. Today will be slightly less zippy. There will be less information today to cover. Because I used to cover today's information and Thursday's information in one lecture, in one hot shot go. And that was way over people's head. So today I will only cover the basics of chemical reactions, and on Thursday I'll cover this terrific thing called stoichiometry. So hang tight. The other thing is, once your midterms are due, it will take me a few days to grade all of them and hand them back to you. So the way it's going to work, I'm already done grading the first 10 that got submitted earlier today. When I finish your midterms, all of them will be in a big fat folder in the front desk with feedback. And it is your job to swing by there and get it, because I'm not going to waste 15 minutes of class on saying, where's the roof sheet? Where's the roof sheet? And then, oh, there's a roof sheet. If you have questions on the midterm, feel free to work with a partner. Feel free to look up the answer online. Most of the questions, you won't ask all the questions, you won't find the answer online because I wrote them. Sorry. And feel free to visit me during office hours. I'm very lonely during office hours. I have like 3 people coming today. Come visit me again in office hours Monday through Friday, 10 a.m. to 2:45 p.m. If you want to stick around after the morning lab tomorrow, feel free. I can shell out any questions you might have. Hello, Ashley. Grab a chair from room 2. Sorry. Again, feel free to visit me during office hours. If you have a pressing question and you can't make it in the weekday office hours, I'm here on Saturday from 8 a.m. to 11 p.m. And also on Sunday from 2 p.m. to 11 p.m. Okay, you can sit right here. Again, feel free to swing by office hours, utilize those. If you have questions about other classes, I can help you in anything with computer science. Don't come to me for your computer science problems. Any other class, I've taught every single class except for statistics. Any of those as well. Swing by, it's free, it's helpful, and it's fun. It's only 2 people at a time. Okay? So today is going to be a little bit different. I have some fill in the blanks. Do we have more handouts coming around? Where are the rest of the handouts? Okay, are they coming? Who has the big stack of handouts? Right. Get one, pass it around so we can begin. Lastly, tomorrow we'll be working through a laboratory experiment that is currently in the peer review process of getting published in the Chemical Education Journal. Please wear closed-toed shoes because you're not working with the beautiful generic solid water. You're working with a solid dimethyl sulfoxide. So you will be in closed-toed shoes, or we will supply you with a pair of Macy's grade cellophane baggies for your feet. Okay? Does that make sense? Okay. Finally, if you are interested in the demonstration that I'm going to do in class today, come on Saturday for the optional lab, and you can sit there and crank out cool chemicals all day. Okay? again, there are more labs in your lab manual than there is time. If you want to do a table surveys, that's up to you. Totally okay. There we go. Okay, where are the leftover handouts? Any leftovers? Do we lack handouts?
Yeah, we ran out.
We ran out? Of which one?
There's more.
There's
What the hell?
Where did we run out of this one? Where did we run out of this one? Okay, you guys figure out we need one? And then we need one of these. Where did we run out of this one? Sorry, that's the 12. Take one pass it. Take one pass it. Okay, no chocolate. Lastly, last announcement. I promise this is the last announcement before we get going. And today we have less material to come. As soon as your midterms are due, there is another assignment that I will assign to you, and you'll get an email for this assignment. There's a fantastic 3-minute long chemistry video online that you will be asked to watch. How long does it take you to watch a 3-minute chemistry video?
4 minutes. 2 hours. Yeah, exactly. So you have to like wait for it to load. It's terrible. And what if your finger?
It takes 3 minutes to watch, but you will also write 10 things in full sentences from them that are related to what we talk about in class. Okay? Anyways, we're going to talk about your quiz first, and then we will talk about all right, here we go. Don't talk over. Ladies, don't talk over. So, make sure you are taking quizzes. Okay, a 1 mole aqueous solution. What is molality? What is molality? Yeah, look at this. Your computer science instead. Molality is moles of solvent per kilogram of solvent. Okay? Remember, in a solution, you have 2 things. You have a solute and you have a solvent. The solute is the thing that's dissolved, and the solvent is the thing that is doing the dissolving. Yes? And molality is one of our ways where we express concentration. What happens in a solution to the freezing point and melt and boiling point? By the way, go home and test your parents of this. I hope no parents are watching this video. But go home and ask your mom, which is higher, the freezing point of water or the melting point of water? And 90% of people in the United States will say, oh, obviously the melting point of water is higher than the freezing point of water. They're the same. Water melts at 0 degrees Celsius. It also freezes at 0 degrees Celsius. What happens to the melting point of a solvent in the presence of solvents? It goes down. Remember, we talked about 2 colligative properties. We talked about freezing point depression. And we talked about, what is the other one? Boiling point elevation. In other words, in any solution, the freezing point is always lower than that of the pure solvent. And in any solution, the boiling point is always higher than that of the pure solvent. Does that make sense? When I ask people questions, they either look blank or they smile. Does that make sense? Yes. And what are our formulas? The change in the freezing point, delta TF, is given by I, the number of particles, times KF, the mole freezing point depression constant, times M, the molality. Now, on tomorrow's lab, you'll be given an unknown white solid, a white powder. You'll be given a little white powder test. I promise it only contains a legal substance, no illegal substances. Anyways, you will determine the identity of the substance based on its effect on the solvent. The boiling point elevation formula is the same. Delta TB, the change in the boiling point, is equal to I times Kb times the molality. Two questions. Why do we use the molality instead of the molarity? Why molality? What does not affect molality? Molality is not, temperature dependent. Molality does not depend on the temperature. Check this out. If you heat up your solvent, you still have X kilograms of solvent. Just because you heat it up doesn't mean you lost some mass. Right? Does that make sense to people? Yeah. Kf is a constant. Now, what is I? When I was writing your text for the summer, I think in the first edition, I had a question, what is I? And Microsoft Word autocorrected to what am I? I'm a human, by the way. But what is I? What does this little letter I represent? Somebody remember the full name of it? This is V, yeah. Oh, the Van Hoff factor. And what does the Van Hoff factor tell us? This is I, right? What does it tell us? Adrian, what is I?
How many parts there are?
How many particles? I gives us the number of particles that something dissociates into in solution. For example, calcium chloride, CaCl2, when this goes into solution, what are we going to get? What are we going to get? We're going to get calcium 2 plus and 2 chloride minuses. And so what is I? Does that make sense? Because every calcium chloride makes 3 things in solution. Does that make sense to people? One of these becomes 3 things. And remember that a colligative property depends on the number of particles. And so if you make more particles, it will have a greater effect, won't it? Yes? Okay. Be interactive, yeah.
So the Van Hoff factor for like salt NaCl is 2?
Precisely.
Okay.
For NaCl, I is equal to 2, because in the solution this becomes a sodium plus ion and a chloride minus ion. What about methanol, CH3OH? Against popular opinion, methanol is not what makes you get drunk. That's ethanol, slightly different. Kabir, what is I for methanol, CH3OH? Nope. Close.
4.
Nope.
6.
Nope. Close.
1.
1. That's correct. Why is I 1? Because it's a molecular compound, and most molecules don't break up in solution. Remember, these are ionic salts. You have a sodium plus a chloride minus. They're already separated. They're going to separate out in solution. But for something like methanol, CH3OH, methanol is a molecule. And so it's not going to break up in solution. It's going to stay as an entity. Does that make sense?
So for glucose, is I 1?
Yep.
Okay.
Because when glucose dissolves, I'm sorry, anybody like making lemonade? Maybe listen to the duck song? Doing the lemonade stand behind you.
Cry, you're in that video.
But if you're making lemonade and you dissolve sugar in water, those sugar molecules are not breaking up when they go through water. They're separating from each other, but the molecules themselves stay as individual entities. Does that sort of make sense? And so I is 1 for any sort of molecular compound. Lithium bromide, LiBr, what is I for lithium bromide?
2.
I is 2, because we form 2 things. We form a lithium plus and a bromide minus. Does that make sense? Now, let's answer this question. I already answered it in the first 2 sections. A 1 molal aqueous, by the way, if you would like to come to the 5 to 6:30 section, there is plenty of room in that section. Please come an hour and a half earlier. You are able. 5 to 6:30. There's only 9 people in that section. A 1 molal aqueous solution of each of the following is made. which has the highest melting point? Let me ask you this. If it has the highest melting point, does it have more particles or does it have fewer particles? Logic this out with me. Remember, chemistry is pure logic. I got in an argument with a philosophy major once in college because he's using philosophy as pure logic. I said, what's more fundamental than philosophy? He said, well, I don't know. I said, chemistry, of course. Logic this out with me. The more particles you have in a solution, the lower the freezing point is going to be. Therefore, the fewer particles you have in a solution, the higher the freezing point / melting point is going to be. So which of these has the fewest, has the lowest concentration of particles? Well, it's methanol, because for methanol, I is equal to 1. You see, because they have the same molality, they have the same Kf. Kf is a property of the solvent. The only difference is I. Right? Does that make sense? The only difference between each of these solutions is I. And the more particles you have, the more they will depress the freezing point. So if you want to find one with the highest melting point, you're going to find the one with the smallest I value. Because it will depress the freezing point the least. Does that make sense? That makes sense? Yeah.
What was that you said 30 seconds ago about the value of I relating to the freezing point and melting point?
I is the only thing that's changing across these 4 options.
Okay.
One molal solutions of calcium chloride, sodium chloride, methanol, and lithium bromide. The only difference between these 4 options is I. If you have a small I, the freezing point will be not as depressed as if you had a big I. Does that make sense? Does that make sense? If I is just 1, then your freezing point will not be as depressed as if I is 2. If I is 2, you have a bigger freezing point depression. Does that make sense? And so to answer this question, which has the highest melting point, it's going to be methanol, because methanol has the smallest I value. Okay? Yeah.
So ionic type compounds would have, they would break up, but then if it was like covalent, it would just stay the same.
Most covalent molecules, 99.999% of them, stay as one thing. Sometimes they break up.
Which ones?
Let me go to number 9. HBr dissolves by ionization. Because HBr, what happens in HBr and molecules like HBr is the covalent bond between the hydrogen and the bromine physically breaks in solution. We call this ionization, where this is why I'm not a basketball player. HBr, there was a covalent bond between the hydrogen and the bromine. You see that? And when this went into solution, this bond physically broke. And we ended up with H plus and bromine minus, bromide minus. And so this is called ionization. Because we form ions by breaking a covalent bond. So these are the only, there's very few cases in which this actually occurs. But this is different from dissociation. Yes?
How do you know when to use
Hold that question for lesson 10. Oh, I'm sorry, lesson 9.
Keep a note.
Yes, keep it, oh, 10, I'm sorry, 10. Okay, any questions about this? Any questions about this? We're gonna skip to number 3. 70% of people got number 3 wrong. Big fat, anybody find that big fat calculation one really confusing? Really confusing? How many of you guys did number 2? Weird questions. Great job, Carolyn. Did you get the structures done? Huh? What? Oh, okay, great. Okay. So let's run through this question together, okay? The mole freezing point depression constant. And can everyone see that screen? Yeah. The mole freezing point depression constant for cyclohexane is minus 20.9 degrees Celsius per mole, and it normally freezes at 4.959 degrees Celsius. The normal freezing point for cyclohexane is 4.59 degrees Celsius. And we know that Kf, the mole freezing point depression constant, is 20.9 degrees Celsius per mole. And the question is, let's say I made a solution by dissolving 0.78 grams, thank you very much, sir, of benzene into 100 grams of cyclohexane. Pretend like that has 46 fixed. The question is, what will the freezing point be? Let me ask you this. Is it going to be below 4.59 or above 4.59? Sonia, what do you think? Think about it. What does a solute do to the properties of the solvent? Does the freezing point decrease? Is the freezing point depressed?
Yeah.
Or is it elevated? It decreases. So if the solvent normally freezes at 4.59 degrees Celsius, what temperature will it freeze at if you add some stuff to it? Below 4.5, right? Somewhere below. And the change in the freezing point is related to the molality in this way. Does that make sense? What is I for benzene? What is I for benzene? Dave, what's I for benzene? Is benzene a molecule or is it an ionic salt? Gentlemen, I'm talking to you before. Is benzene a molecule or is it an ionic salt? It's a molecule. If it's a molecule, is it going to break up in solution or not?
No.
If it doesn't break up in solution, what's I?
1.
So we know that I is equal to 1. And we're given Kf. We know what I is, we know what Kf is. Can we find the molality?
Yes.
Can we find the molality? The molality is, again, the moles of solute per kilogram of solvent. How many moles of solute do we have? Can we figure that out? Actually, how do you find the moles of solvent? Actually, before we answer that, who's the solute and who's the solvent? Who's the solute and who's the solvent? What is the solvent? Is it the stuff that's being dissolved or the thing that's doing the dissolving? I see. The solvent is the thing that's doing the dissolving. So the solute is the thing that is being dissolved. Does that make sense? Here's our solute. Here's our solvent. In other words, we have a solution made by dissolving benzene into cyclohexane. Does that make sense? The solution is composed of a solvent of cyclohexane with a little bit of benzene put into it. Devita, what's molality? Okay. Now, we know that we have 0.1 kilograms of solvent, right? Isn't that what this is, 0.1 kilograms? Our solvent has a mass of 0.1 kilograms. How do we find the moles of solvent? Can I convert 0.78 grams of benzene into moles? how do we get from grams to moles? We use the molar mass. And how do we find the molar mass? So we add up the atomic masses of all the elements, right? One carbon is 12.01, and one hydrogen is roughly 1.01. Hence, the molar mass of benzene is roughly 78.12 grams. Does that make sense? We've converted the grams to moles by using this conversion factor that 1 mole of benzene has that particular mass. Does that make sense to people? Does that make sense to people? Wow, you can refill my coffee. It's very bad for you to drink that today. Okay. Somebody calculate the molality in your head. You do it in your head 10 minutes. Ashley, what's that molality going to be?
I don't know.
Think about it. What's 0.78 divided by 78?
Not really.
This is like 0.01, right?
No. Yeah.
Divide that by 0.1, that's like 0.1, right?
Yeah.
Somebody throw this in the calculator and show me that we get 0.1. If you threw it in the calculator, you get 0.1. For the sake of time, we're going to move and plug into this equation. I is 1. Kf is 20.9 degrees Celsius per molal. And the molality is 0.1 molal. Therefore, the delta T is 2.1 degrees Celsius. That is the change in the freezing point. Do you see how we piece this problem here? This is, hey guys, this is a tough problem. If you saw the problem, you're like, I don't know where the heck to start. That's okay. This is a tough problem. Okay? But I want you to sort of think about how we can use an equation. Check this out, guys. We're beyond the days of plugging and chugging, where I gave you 3 of the 4 unknowns and you find the 4th one. Think about why the math makes sense, because it does. If this one is tough, that's fine. This is tough for everyone. In fact, this is tough for my chemistry students, because it came out of the chemistry book. But think about it. Yes, does this setup make sense? Does anybody have a question about this setup? Now, check this out. If our original freezing point was 4.59, and we depressed our freezing point 2.1 degrees Celsius, this is the change in the freezing point. What is the new freezing point? 2.5. A lot of energy back there. 2.5 degrees Celsius. Does that make sense? And so your answer would be 2.5. Any questions about that? So those are a few that I wanted to work through. For the sake of time, we're going to move on to today's lesson. Again, if you have issues, everybody has issues, I have issues. Anybody have issues? We all have issues. Say, I have issues. This is the one chance you have to talk over me. Say, I have issues.
I have issues.
Great. If you have issues, come visit me during office hours. I'm very lonely during office hours. Okay, so today, don't talk over me. We're talking about chemical reactions today. And today should be relatively more simple than the last few lessons. Today should be pretty straightforward. The morning class today was easy breezy. Who's ever heard this? Check this out. Who's ever heard this? Baking a cake is a chemical reaction because you can't unbake the cake. Who's ever heard that? Who's ever heard that? Or cooking an egg is a chemical reaction because you can't uncook the egg.
Yes, you can.
You
You get a new egg.
Now, check this out. Two correct statements. Baking a cake is a chemical reaction. Check that out. The unbakeability of a cake is also a fact. Right? Anybody ever tried unbaking a cake? Good luck. How did you unbake a cake?
I never baked it.
Yeah, we make it.
No? Okay. Check this out. Two true statements, poor logic. It's not the fact that you can't unbake the cake that makes baking the cake a chemical reaction. In other words, most chemical reactions are actually perfectly reversible. Some of my synthesis students this past weekend were making some molecules. They were making molecules, and all of a sudden, they decided to accidentally add some water prematurely, and that reversed about 3 hours worth of chemical reactions. Fine. And so they got set 3 hours behind. Most chemical reactions are reversible. It's not necessarily the case that just because something's irreversible, therefore it's a chemical reaction. Likewise, it doesn't necessarily follow that if something's a chemical reaction, it must be irreversible. So those are two true statements. Baking a cake is a chemical reaction, and you can't unbake a cake. But it's not a cause and effect relationship. So when somebody says to you, baking a cake is a chemical reaction because you can't unbake the cake, what's your response? Well, both true statements, but that's not the why. What makes something a chemical reaction? What makes something a chemical reaction? Is boiling water a chemical reaction?
No.
Something that's irreversible?
It's a change in the chemical composition.
There's a change, something to read. I recommend that you read the reader before you come. A chemical reaction involves a change in the composition, in the chemical identity of the substance. For example, I'm going to use this as an example. Who ate salty food today? Anybody eat salty food today? Only 5 people in this class ate salty food today. How many of you ate salty food today?
Everybody.
Everybody did.
Everybody.
And salts and
Some of you
everything.
just drink water and eat like unsalted saltine crackers.
She honestly eats plants.
Just eat rice and water all day. That's terrible.
The rice and
Check this out. Sodium. Anybody who remembers what happens when you put sodium in water last week?
It blows up.
It blows up. It actually blew up my glass beaker.
Oh yeah.
In the morning section, we took my glass beaker and it smashed into a snowball.
Oh,
Yeah,
that was fun.
that was fun. It was very fun.
Have to clean up.
Chlorine gas is highly toxic. It's a green gas that will kill you if you breathe it. But you mix it together in a reactor form NaCl in the solid state, and that's something you put in your baked potato. So you take an explosive metal and you combine it with a toxic gas, and you get this white crystal that you can eat. Isn't that crazy? The idea here is that in the chemical reaction here, the first one, atoms are rearranged. Atoms are rearranged. In the chemical reaction, atoms are rearranged such that the chemical identity of the products is different from the chemical identity of the reactant. Okay? What's up?
Nothing.
In a chemical reaction, the atoms are rearranged. I'll give you this as another example. When I was a freshman in high school, back when Mission San Jose had really crummy pavement in its parking lot, we were running along, and there was like a crack in the parking lot that I swear was like a quarter mile across. Anyways, my friend tripped on it and got a big road rash from his knee to his ankle. Huge road rash. And so we were just looking at him like, his name is Omar, and he's sitting there bleeding his leg out, and we're like, oh shoot. And so we go, so then we go to the locker and we get a bottle of hydrogen peroxide. Hydrogen peroxide, when it hits your flesh, it starts to bubble. In this reaction, hydrogen peroxide will yield water and oxygen, and in this process, it will destroy bacteria. So here's what we did. We opened the bottle, it was unopened, and we poured the whole darn bottle all over his leg. And his leg's like bubbling, you know. Yes?
Science experiment.
The AQ.
What is the AQ?
I'm gonna get there in a moment. Hold your breath. And so his leg was like bubbling in red like a big volcano, and he was like screaming his head off too, because it was like, who likes a bubbling leg? Yeah, he's like, I'm gonna die! Like running around like a bubbling leg. Anyways, that's a chemical reaction, because check this out. Here are our molecules in the universe. Here's a molecule of hydrogen peroxide. Here's another molecule of hydrogen peroxide. When these two react, they form two molecules of water. What is the geometry of water, folks? And one molecule of diatomic oxygen. That's a yeah.
Why don't they react inside the bottle?
Ah, because they react inside the bottle, which is why hydrogen peroxide has an expiration date. Go to Walmart tonight with mom and dad and look at the hydrogen peroxide in the medicine aisle. There is an expiration date, but it's just very slow. There's something called an enzyme in your cells called peroxidase, which makes us go 10 times faster, which is why Omar's leg is bubbling like a volcano. Now, check this out. The atoms themselves stay the same. The only difference was that they are rearranged in the way that they are bonded to each other. They played musical chairs, if you will. Anybody like playing musical chairs? They're all game. Anyways, we should play musical chairs. Okay, in a chemical reaction, atoms are rearranged. A chemical equation. This is a chemical equation. It shows the relative ratios of each species involved in the reaction. In chemistry, when we say species, we don't mean cats and dogs and bats and rats and hogs and mouse. We mean different chemicals. So if you were to balance these, check this out. I'm going to say 2 molecules of hydrogen peroxide yield 2 molecules of water and 1 molecule of oxygen. The chemical, these are your fill-in. The chemical equation shows relative ratios of each species involved in the reaction. The chemical equation shows relative ratios. Okay, the first one is in the chemical reaction, atoms are rearranged. Here's what we mean by ratios. Check this out. On the one hand, I can say that 2 molecules, look up here, 2 molecules of hydrogen peroxide will react to form 2 molecules of water and 1 molecule of oxygen gas. I can also say that 2 moles of hydrogen peroxide yield 2 moles of water and 1 mole of oxygen gas. Does that make sense? These are simply ratios of numbers. These react in a 2 to 2 to 1 ratio. Does this make sense? Yeah. Oh, pass this back. I apologize for the crummy printing. Watch this. These things going in are called the reactants. The reactants are the things going in. And the things coming out, this is your next filter one, these are the products. Okay? The reactants are the things going into the reaction. The products are the things coming out. Anybody does research with Alicia Makaru on flies? I wonder if that's one of her blind flies that came out in the quad. I think we do research with Alicia. Yeah, she does like blind or sophalo, no eyeballs. Crazy. Whatever. I don't know how they see where they're going, but they probably don't see it. So reactants. The substances entering a chemical reaction are called the reactants, and the resulting compounds formed from the reaction are called products. Okay, reactants and products. Make sure that is drilled in here. Okay? The next blank, the law of conservation of matter. The law of conservation of matter. Check this out. We can't have atoms coming out of nowhere. And we also can't make atoms disappear into nothing. According to the law of conservation of matter, matter is neither created nor destroyed in a chemical reaction. The net quantities of each element stay the same before and after the reaction. Yeah,
If you can't create matter, where did matter come from?
it's a very deep question. That is not a chemistry question, that's a
Jesus.
philosophy question. That's what I said in the accident. Chat later, though. Very good question. Does that sort of make sense? Check this out. How many oxygen atoms did we begin with? 1, 2, 3, 4. How many did we end with? 1, 2, 3, 4. Does that make sense? We started with 4 oxygen atoms and we ended with 4 oxygen atoms. Yeah? Does that make sense? Victor, how many hydrogen atoms did we start with and how many did we end with? We started with 4 hydrogen atoms, right? 1, 2, 3, 4, and we ended with 1, 2, 3, 4. Yes? The number of atoms of each element does not change. Okay. Balancing a chemical equation involves manipulating the coefficients. The coefficients are these numbers here. The coefficients. Involves manipulating the coefficients of each compound such that the number of atoms in each element is conserved. Okay. So we have to make this a 2, and we have to make this a 2 so that the number of hydrogen atoms before and after, and the number of oxygen atoms before and after would be the same. Does that make sense? Just by show of hands, how many of you have done balancing chemical equations sometime before in your life? Most of us should have seen balancing chemical equations. But when we balance a chemical equation, we add coefficients that allow us to conserve the number of atoms of each element. Okay, here next to each species, here's your next blank. States of matter are indicated in italics next to each species. Now, you guys asked a very good question earlier, what does AQ mean? AQ stands for aqueous. It means it is dissolved in water. Aqueous means that it is dissolved in water. Aqueous. Any questions about that? All good, so yeah. Again, a species in chemistry simply means a chemical. We don't mean like dogs and cats and those things, it just means chemical. Somebody who thinks. Okay? There are different types of chemical reactions. As we go through today, I'd like you to sort of be thinking about these different types of chemical reactions. And today should not be rocket science, actually you meant rocket science, but it should not be terribly difficult rocket science. It's simply applying some previous knowledge and getting to know chemical reactions. Check this out. If you've been enjoying our talk about electrons, about geometries, about orbitals and all those things, that's fantastic. But from here until the end of the course, we're talking about reactions. We're talking about reactions. So get used to talking about reactions. Here we go. The first type of reaction is synthesis. We'll talk about synthesis, we'll talk about decomposition, we'll talk about single displacement, double displacement, combustion. Then if we have time, we'll talk about redox. Okay. So let's begin by talking about synthesis. Now, my background is sort of synthetic chemistry. Does somebody want to tell me what does it mean to be talking about synthesis? What is synthesis? Yeah. Yeah. Aqueous means it's dissolved in water. So soup, next time when your mom makes you some soup, whose mom made soup today? Or sometime this week? So actually, when you go home, tell your mom, thank you, Mom, for this aqueous sodium chloride solution with junk floating. It is dissolved in water. So I'll be doing a quick demonstration in a moment that involves two aqueous solutions. In the synthesis reaction, we take two smaller things and we make something bigger. Maggie, have you ever left your bike out in the rain? No. Who's ever left their bike out in the rain? What happens if you don't wipe it off? It rusts. And check this out. Here's why rust happens. Iron, which your bike is made of, and the solid state will react with oxygen in the air to yield iron 3 oxide. By the way, this is one of your questions in the midterm. What is the chemical formula for iron 3 oxide? How do you know it's Fe2O3?
Because the iron, each of the two has a charge of 3 plus.
The 3 there tells us that iron has a charge of 3 plus 3. And the oxygen, we know, will have a charge of -2. So if you have iron with a 3 plus and an oxygen with a 2 minus, the only possible ratio in which these two can combine is a 2 to 3 ratio. Does that make sense? Fe2O3 is iron dioxide. So in synthesis, we take two smaller things and make one bigger thing. There we go. Generally speaking, we can have A plus B equals B. By the way, you can take notes about this on the back of your sheet, the little chart, or you can take notes on a separate sheet of paper. Awesome. I'd like you, real quick, with a partner, balance this equation. Balance this equation.
This one?
That one?
This one? It's What are we doing? The ratio.
What are we doing? So long.
Just multiply both sides.
What are you doing? Balancing the equation?
Yeah.
Wait, I don't know.
So it's like
Okay, so you have Fe, and then
break it up.
O2, that's on one side, and the other is Fe2O3. That's a single molecule, and those are two.
Can you break it up? Can you break it up? Are you allowed to do that? No, you have to move on to the same thing. Yeah. So there's 3 Fe plus. So it's, no, it's 2 Fe. No. It's 2 Fe plus 3.
NGSS, who said that?
No.
We love NGSS.
Wait, Edward,
O2
can you really quick explain the O3 on the right? I don't understand that.
In order to balance these
So then you would have to do
you have to have 2 of these and 3 of these.
Yeah, exactly.
And so therefore we have Fe2O3, there's 3 oxygen ions, 2 oxygen.
Okay. Okay, all right.
I like how you already.
You can't help it. How am I supposed to balance the 3 though?
No capital.
if we give them that and then like
All right, here we go. Check this out. Somebody want to offer us your coefficients to balance this? Let's see. D2, give us your coefficients. Give it a shot. Even number, odd number, what's the first thing we should do with this side? 2, and this will then become 3. There are 6 oxygen atoms, therefore there have to be 6 on this side. What happens with iron? 4, perfect. No problem. 4 atoms of iron react with 3 molecules of oxygen to yield 2 units of iron dioxide. Or we can say 4 moles of iron react with 3 moles of oxygen to yield 2 moles of iron dioxide. Because there were 3 molecules of O2, we need that to balance it out. You can't divide them by 2. So, there were 4 iron atoms to react. Therefore, you need 4 iron atoms to begin with.
And 6.
On the left side, you have 4
very
irons
dramatic.
and 6 oxygen. On the right side, we still have
Yeah, now I can
4 irons and 6 oxygen.
I'll say unit
I don't think I'm not.
By the way, yeah.
Would it have worked if you took the iron oxide and just left it as one compound? Like instead of putting 2 on it? I mean, with the 2 in front, the
So why can't let me back up.
coefficient?
Why don't I just say 06?
That's not. That's not conservative.
Yeah, because the unit is Fe2O3. The unit is O2. We're saying you have 2 of these things. Does that make sense? Okay. The next kind of reaction is a decomposition reaction where we take some more complex compound and we break it down into smaller substances. Okay? For example, mercury 2 oxide, HgO, when you heat this up, will yield mercury in the liquid form and oxygen gas. Okay? We took something more complex. By the way, an arrow with a triangle with arrow means that you heated it up. Yeah. I'm sorry? Heat. So if we took mercury 2 oxide and we heated it up, we would yield liquid mercury and O2 gas. I'd like you to balance this.
So it's there.
It's not valid.
It's not valid.
No, you have an O2.
O2, you don't
Yes.
It's already valid, so.
No, it's not.
So you just make it 2 HGO.
Two of the large.
So you just make it 2 and make 2, right?
Yeah, two. Both of them.
That makes sense. Wait, why would you figure that out? Guy, I wonder what it comes to. Jayon, are you actually working? Yeah, look to your left. Look at the TV. Look at the bottom.
Wait, this, right? It's this. AJ, this thing.
All right, who has our coefficients?
It's
You put 2 on the big thing, and then you put 2 on the first level, and yeah.
It's definitely not on the level.
Does that make sense? Why can't I just have each be 2? Why do I have to say 2 each be? Yeah. Oh yeah, what's your question? Solid and gas. Yeah, so the states of matter. The states of matter are indicated in the color. Does that make sense? Here's the next one. This is kind of fun. Imagine we had some element A that asked some element B out to win a ball. And so they went out to win a ball. And then they bumped to element C. And element C walks up and says, hey, screw you, B, and displaces B. A and B and win a ball, and bumps into C, and now we got A, C, and B.
Whoa, that's rude.
This is a single.
That's so much disrespect. Wait, that's so
You
much
got kicked
disrespect.
out, man. I feel bad for you.
You wanna go be friends with me?
So check this out. For example, aqueous copper chloride, CuCl2 aqueous, will react with zinc in the solid form to yield zinc 2 chloride aqueous and solid copper. That is a single displacement reaction where one element displaces another element. It's not just like that. Displaces another element. Okay? Make sense?
Do you have to balance that?
This is already balanced.
Okay.
Now, check this out. Who had soup today? I think I asked you.
Somebody.
So maybe so maybe your mom made you soup. Who eats soup? Who drinks soup? If you're eating your soup, there's something wrong with it.
I drink water.
If you're drinking your soup, let's say you're drinking your soup. Soup is just salt water with junk floating in it, isn't it?
Yeah.
Parents are watching this video, I hope you don't get offended. And let's say you're drinking it with an aluminum spoon. Anybody drink soup with an aluminum spoon? Why doesn't this reaction occur? That'd be kind of bad, right? Why does this reaction not occur? Yeah, kind of bad if you were like drinking your soup happily and your spoon started dissolving and making solid sodium. That'd be kind of bad, wouldn't it? That'd be terrible, right? Why does this not occur? Gary, why do you think this reaction not occur? Okay, ladies and gentlemen, don't talk about it. Right there. Why does this not? This is the single displacement reactant, isn't it? Why can't aluminum the bachelor kick out sodium? Why?
More.
Somebody did the reading. Find
Me too.
a sheet that looks like this.
I was reading that.
This is the chili pepper ratings of metals. Different metals have different activities. Okay? Check this out. The higher we are on the activity series, this is the activity series. The higher an element is on the activity series, the more active it is, and the more likely it is to displace somebody else. Check this out. Where's zinc and where's copper? Where's zinc and where's copper on this table?
It is the ninth one.
Where's zinc and where's copper on that
Zinc's in
table?
the middle, copper's at the bottom.
Zinc is the
Who's
ninth.
higher? Who's more active? Zinc
3
or
and solid.
copper?
Zinc.
So zinc is more active. He's gonna be like, see you later, copper. Who's more active, sodium or aluminum? So can aluminum displace sodium?
No.
No. So here's your next fill in the blank. Skip one. I'll get to that question in a minute. Here's your fill in the blank. A single displacement reaction will occur. Everybody find that fill in the blank? A single displacement reaction will occur if a metal that is higher on the activity series displaces a less active metal. Okay? The activity series tells us whether or not a single displacement reaction will actually occur. The reason why your aluminum spoon doesn't start dissolving in your hands is because of the activity series. Okay? Thank goodness for the activity series, right? Yes.
What makes these elements like react or less reactive? Like, what about them?
What makes lithium, sodium, and potassium very reactive, and these guys not very reactive? These guys have one valence electron. Super easy to lose. These guys have more than one valence electron. They're just chilling.
Okay, gotcha.
You'll see the top elements of the activity series are your group 1 elements with only one valence electron. They're very reactive. Okay, so does that sort of make sense, people? Tanishka is so happy about single displacement. She's texting your mom, thank you for the single displacement, for the activity series. My aluminum spoon doesn't dissolve when I'm making your soup.
Yeah, I'm Snapchatting my mom.
Wow.
Okay. So here's a single displacement reaction. Isn't that cute? Now, we're moving on. Now let's say A asked, listen, let's say A asked B out to win a ball. And C was like, okay, I should probably ask someone else too. So then C finds somebody named D, and C asks D out to win a ball. And then while they're at winter ball, D gets set up with C. He's like, screw you, C, you're so boring. And so D is like, yeah, screw you, B too. And so then we get A, D, and C, B. This is a double displacement reaction where I like to say the two dating couples swap dates.
It happens in the real world. Mr. Steele.
I don't want to know. Please do not tell me about your life.
Oh, sorry.
Everyone has issues, remember?
Let me give you this as an example. Listen up. Potassium iodide, in the active state, will react with lead nitrate in the active state to yield lead 2 iodide in the solid state and potassium nitrate in the active state. Check this out. This is an example of a double displacement reaction. Because initially potassium was having a swell time with the iodide, and lead was having a swell time with the nitrates. And at the end of the reaction, lead's having a swell time with the iodide, and potassium's having a swell time with the nitrates. What's strange about the states of matter here?
It goes to solid.
It goes what?
The liquid turns to solid.
Yeah, something goes solid. So I have here a beaker here, and we're gonna do some lead nitrate. This stuff is pretty toxic, so I do not recommend trying this at home. Okay. So lead nitrate is a little funny because there's some trouble in there. So we tend to find that. Don't try this at home. So here's some lead nitrate. It's not pretty. It's clear. Look, it's good enough to drink. And here's some potassium iodide. Look, isn't that pretty? Clear enough, good enough to drink. And when we mix the two together, we get something cool that happens.
Whoa.
That's a watered down mustard.
This is like melted Laffy Taffy, isn't it?
What the?
Hey, someone needs to cook
Now, check this out. I'm gonna let this settle for the rest of the class. What is that? Is that a liquid or is that a solid? So, this yellow thing that's coming out is lead iodide. This is what we call a precipitate, okay? Two aqueous solutions reacted and formed something that was insoluble. Here's your next building block. A precipitate, actually this is one right before. A precipitate forms when an insoluble combination of ions are combined. A precipitate forms. A precipitate is spelled this way. Here's our precipitate. A precipitate forms when two insoluble ions are combined. That's kind of cool.
This is what added.
A precipitate forms when two insoluble ions are combined. Lead iodide is insoluble. Okay? That was kind of cool. How many of you thought that was kind of cool? A precipitate forms when an insoluble combination. Insoluble means not able to be dissolved. Lead iodide is insoluble in water, both by and large. A precipitate forms when an insoluble combination of ions is mixed. I do not recommend drinking this, although it looks really cool. Here's another very fun thing that we're going to do. Here's another very fun thing that we're going to do.
It's proportional. You want to make it?
You guys are gonna win in like 2 or 3 years. You guys are gonna win.
As soon as I get all this nasty. By the way, anybody like hot yellow Corvettes?
Clyde?
What do you think they use in yellow paint to make a Chevy Corvette?
That thing.
Yeah.
So here's the next example. Again, don't try this. Okay. I have some sodium phosphate here. It was supposed to be clear, but then it got contaminated with lead. And this is iron. Isn't that beautiful, like maple syrup? Amber, golden, fantastic. When you mix them together, you get some nasty, disgusting precipitate that comes out. That's a
So
solid.
this is Coke.
Okay, let's start the bottle. Anyways. A precipitate forms when an insoluble combination of ions is mixed. Okay? A precipitate forms. Let's talk about how we know whether or not something is insoluble. Let's talk about whether or not we know how we know whether or not something is soluble. There are certain rules of solubility. Your book has an overmuch of rules. And if you like a lot of rules, I don't like a lot of rules, so I'm going to boil it down to Edward's 3 rules of solubility. So hang tight. I'm going to boil down solubility to 3 statements. Okay, here are your 3 statements. Number 1.
Sounds like Butler.
All nitrates. Actually, voice should not be coming in my ears. Nitrites, I do call people out. These are acetates, ammonium, and group 1 salts are soluble. Always. So, lead nitrate was soluble. Iron nitrate is soluble. Sodium chloride is soluble. Ammonium nitrate is soluble. Okay? rule number 1. Here's rule number 2.
What are these called? Edwards rules of science?
Edwards solubility rules. I'm not soluble. If you put me in a swimming pool, I'm not going to dissolve against your wishes. But here's number 2. Most, sorry, that was really random. Most sulfates, sulfites, fluorides, chlorides, bromides, iodides are soluble, except in heavy metal salts. For example, copper sulfate is soluble. We'll say copper sulfate is soluble, but silver sulfate is insoluble. Okay. My last rule of solubility. Most hydroxide salts, carbonate salts, phosphate salts, oxalate salts, and sulfide salts are insoluble, except group 1 and ammonium. So sodium phosphate, that was what I just dumped in there. That was soluble. But iron phosphate, the milky brown thing, that's insoluble. Okay? I hope you're connecting the dots. Who's ever had a kidney stone or known somebody who's gotten a kidney stone? Why do people get kidney stones? Do people randomly eat rocks and they end up in the kidneys? No. Here's why people get a kidney stone. Kidney stones are large calcium oxalate, which is soluble or insoluble? Insoluble. So that can just on the beaker. Imagine that happening in your kidneys. Ooh, right? You get the little rocks that are. So a kidney stone occurs when you have a precipitation reaction in your kidneys. Any questions about solubility? Here's the last type of reaction I'd like you to know, combustion reaction. How many of you came here in a vehicle that was not powered by electricity?
What if you
A gasoline vehicle. How many of you live in the United States? And you live in a country that relies largely on combustion reactions.
México es mi casa. Casos de amigos.
So, here's what a combustion reaction is. In a combustion reaction, some sort of organic molecule, some sort of hydrocarbon is burned in the presence of oxygen to yield carbon dioxide and water vapor. Okay? In a combustion reaction, a hydrocarbon is burned in the presence of oxygen to yield water vapor and carbon dioxide. Okay? In other words, some CXHY will react with oxygen gas. And what are the products in combustion? Always, this will be carbon dioxide and water vapor. If you look at the fill in the blanks, here's our last fill in the blanks. The last two fill in the blanks. Combustion reactions involve the burning of a hydrocarbon. A hydrocarbon incidentally has hydrogen and carbon
Okay.
in the presence of oxygen to yield carbon dioxide and water. Carbon dioxide
Okay.
and water are always the products of combustion reactions. On a cold day, when you're preparing to start the car, what do you see coming out of the muffler? It's not smoke, it's steam. Because the idea here is when you start an internal combustion engine, all that water vapor being produced in the combustion is condensing because it's so cold outside. Okay, so in a combustion reaction, you have a hydrocarbon reacting with oxygen to carbon dioxide. Any questions about that? So again, if you have your mid-term and it's completed, you can leave it on this little wooden thing on your way out. For tomorrow in lab, bring closed-toe shoes. Tomorrow we will be working through dimethyl sulfoxide. Yes.
What are the last 3 words?
So, balancing by dealing with carbon and hydrogen first and oxygen last. You balance these by dealing with carbon and hydrogen first and oxygen last. And the reason why that is so is because all the carbon here makes it to carbon dioxide. All the hydrogen makes it to water. So with that, I hope you guys have a fantastic evening. If you have questions, listen up. If you have questions for your midterm, if you need help solving a particular problem, send me an email. Thank you very much.